Okay, I mean, this was a very brief introduction to the concept. Most of the concept that I touched upon will be considered in the rest of the course, obviously. So what you find in this introduction can be better understood at the end of the course, because we will see some aspect in more details. And I repeat, the focus is on digital beamforming. Okay, I mean, to understand the various signal processing methods, it's important to derive the array data model. And it is fundamental to understand what are the assumptions under which the data model is derived, because the assumption determines also the limits of application of the model. So this is a fundamental aspect. Now, to derive the array data model, let's assume we have an array of M sensors with any geometry, linear, planar, fully dense, sparse, or thinned, whatever. So we have M sensors distributed in space. And then we have, if we are talking about active sonar or active radar, we have K targets that reflects back part of the transmitted energy. But we can also, I mean, this scenario can describe a passive, an array of passive sensor, for example, acoustic sensor, underwater sensor, where we have K sources of signal and M passive sensor. So the signal is not generated by the sensor. The sensors are passive, not active. In this case, the signal is generated by the sources. So this can be sources of targets depending on if we are in an active or passive scenario. Okay. So the scope here is to determine the power distribution in space. Sometimes this is called also spatial spectral analysis. The concept is similar to classical spectral analysis, where you want to estimate how the power is distributed in frequency. Here, we want to understand how the power is distributed in space, because we want to identify different targets located in different positions in space or different sources. Now, to derive the data model, we start from some simplifying assumptions. It's important to understand what are the implications of this assumption. And this is important to be able to remove at some point some of this assumption and achieve a more complex model, which is obviously more realistic. But let's start first from this simplifying assumption. We have three assumptions, okay? The first assumption, as I said before, the sources or the targets are in the far field of the array. So we are not in the near field. We are in the sources are in the far field. What does it mean? It depends on the frequency. Basically, we can make this assumption if the distance from the sensor to the source, so ds is the distance from the sensor to the source, is much greater than 2 times the diameter of the array square divided by the wavelength. And so the higher is the frequency and the larger should be the S, because the frequency is inversely proportional to the length, wavelength. So the larger is the wavelength, and the smaller can be the distance that allows us to make this simplifying assumption. So it depends on the frequency content of the signal. So lambda is the wavelength that corresponds to the central frequency of the transmitted or generated signal. The second assumption is that our sources that are in the far field can be modeled as point emitters, or sometimes they are called point-like targets. So basically, we assume that the signal is generated in a point, not on a surface, not on a volume. The third assumption is that the propagation medium is homogeneous, so it is not dispersive. So basically, this assumption implies that when the waveform propagates, it doesn't get distorted, so it remains planar. So why these three assumptions are useful? Because as a consequence of this assumption, we can consider the waves impinging on the array as planar waves. And this simplifies a lot the model. The second consequence is that if the source in the far field, we can estimate the direction of arrival, but in a passive scenario, we cannot estimate the range. The range you have seen with, I don't know if you have attended the course of Professor Greco last week. If you have an active radar, you can estimate the range of a target by estimating the time of arrival of the reflected signal. But in a passive scenario, because you don't know when the signal is transmitted, even if you estimate the time of arrival, you can't estimate the distance of the target. You can only estimate what is called angle of arrival or direction of arrival. And this quantity is basically formed by two angles, the elevation and the azimuth. So the direction of arrival consists of the elevation and the azimuth. If we are not in the far field, the waves are spherical, and so in that case, the location of a source is determined by azimuth, elevation, and range. And so we can also measure the range, but the processing is more complicated, and we need a three-dimensional array. But I repeat, I mean, for lack of time in this course, I will consider only sources in the far field. So we will make the planar assumption, and we will see how to estimate the directional arrival of a source. Okay. Let me mention the other two simplified assumption, and then I think we should make a break. The other two simplifying assumptions are that the number of sources is known. Clearly, it is never known. The problem of estimating the number k of sources is called model order selection or detection problem. And I don't have time to talk about model order selection methods. There are a number. IC, archive information criteria, MDL, minimum description length, and others. We will say something about the detection problem later on. So to derive the data model, we make this assumption. K is given. So it's given because we have already estimated. The last simplifying assumption is the following, and then we make a break. The receiving sensors, so all the hardware in the receive sensor, filters, amplifier, etc., can be modeled as linear time invariant systems. So linear time invariant filters. And as you know, any linear time invariant filter is perfectly characterized by the impulse response, or in the frequency domain by the frequency response. And the other assumption is that the geometry is perfectly known. So we know exactly what are the location of the sensor in space. Now, assumption 5, so we know the frequency response of each sensor, and we know the location of each sensor, is equivalent to say that the array is calibrated. So when we say that an array is calibrated, we mean that we know the geometry of the array perfectly, and we know the frequency response of each sensor of the array. Okay. I think we should make a 15 minutes break now. Can you hear me?
Okay, Prof.
Can you hear me? Badri, are you there?
Sir, I think we can hear you as audience, but I think the moderator is not available.
Sorry, can you repeat?
You are audible to the audience, sir. Probably the moderator is on mute or something.
Okay, so if you agree, we make a 15 minutes break now.
Yes, sir. We will take a break of 15 minutes as per schedule. So,
Okay.
So shall we start now?
I think we can start, yes.
Thank you, sir.
Thank you.
Okay, so remember, our goal is to find the array data model. So what is the model of the data that we receive at the output of the M sensors? In order to derive this model, we made 5 simplifying assumptions. Now, some of them will be removed later, but let's start with these 5 simplifying assumptions. Obviously, none of them is perfectly satisfied in reality. But it's important that we start from some simplifying assumption and we understand well what assumption we have made to come up with a model that then can be usefully used to design the processing algorithms. Okay. So to proceed on, let's consider first the single source scenario. So we assume that there is a source in the environment. This source generates a signal, and we define one of the sensors in the array as the reference sensor, and the location of the reference sensor that we call sensor 1 is the reference point, the so-called reference point. Okay, so we denote by x of t the signal that is measured at the reference point, so the location of the first sensor of the array at time t. Then the same signal is received at the M sensor with a delay that we call tau m. So tau m is the delay between the time the signal is received at the first sensor to the time it is received at the nth sensor. Okay. Then we denote by hm of t the impulse response of the M sensor. Remember, we assume that each sensor behaves like a linear time invariant filter. So it is fully characterized by the impulse response, and hm of t is the impulse response of the mth sensor. And then we denote by w tilde m of t as the noise at the M sensor output. It can be thermal noise, can be ambient noise, clutter, reverberation, etc. I mean, any disturbance which is different from the signal of interest x of t generated by the single source. So x of t minus tau m is the signal received at the input of the M sensor. If the M sensor behaves like a linear time invariant filter, as you know, the output of the M sensor, so at the output of the M array, of the M antenna element, is the linear convolution between the input signal and the impulse response of the sensor. So the assumption that the system behaves like a linear time invariant system as a consequence that at the output of the M sensor, what we obtain is the linear convolution, which is represented by this symbol, between the input signal and the impulse response. And then we have additive noise that can be thermal noise generated internally to the sensor, but it can also be clutter, for example, in radar, generated externally from the sensor. So let's assume for the time being that we are in a passive scenario, but everything you will see is valid also in active scenario. So at the end, we want to estimate the directional arrival of the source. Now, as you will see, the directional arrival of the source affects the values of this delay, tau m, for m equal to 1, 2, 3, 4, up to m. Obviously, tau 1 is equal to 0 because the sensor number 1 is the reference sensor. So by definition, tau 1 is equal to 0. Now, because the other m minus 1 delays, tau m, depends on the directional arrival, if we estimate the delays, we can get an estimate of the directional arrival. So from this point of view, the problem of estimating the directional arrival is somehow equivalent to a time delay estimation problem. Now, in a passive scenario, x of t is unknown because it has been generated by the external source. In an active scenario, we know what is the transmitted signal, but what we receive is a distorted version of the transmitted signal. So the received signal is only partially known. For example, it can have a complex amplitude, so amplitude and phase different from the transmitted, obviously, because during the propagation, during the interaction with the target, the signal is attenuated and phase shifted. And then if there is a relative motion between the transmitter and the target, because of the Doppler effect, the signal undergoes to also a Doppler shift, so a shift in frequency. And so in an active scenario, the received signal is partially known. So it's a known function typically of unknown parameters. And the unknown parameters brings information about the kinematics parameter of the target, range, directional arrival, radial speed, and so on. Now, let's make a fundamental assumption. Let's assume that the signal is narrowband, and we know the central frequency Fc. So I think you know that if a signal is narrowband with central frequency Fc, this signal can be represented in this way as x of t equal to alpha of t, which is the envelope, cosine to pi fct plus phi of t, which is the phase. And if x of t is narrowband, it can be shown that the amplitude alpha and the phase phi are low pass signals f. And if they are low pass, it means, so if they have a narrow band, it means that both alpha and phi changes slowly. And the implication is that we can assume that within a time equal to tau m, both the amplitude and the phase does not change significantly. So we can make this assumption. Now, if you consider tau m as the largest delay, basically this assumption means that during the time that it is necessary to the waveform to go through, all the array, the amplitude and the phase does not change significantly. So the change can be neglected. So basically, this is the implication of the narrowband assumption. When this assumption can be made, basically, this assumption can be made if the relative bandwidth, which is the bandwidth of the signal divided by the carrier frequency, is small enough. Small with respect to what? Basically, it has been proved that the narrowband assumption is accurate if the relative bandwidth is much smaller, so 1/10, for example, of the reciprocal of pi m, where m, remember, is the number of sensors. Roughly speaking, I repeat, the narrowband assumptions implies that if the maximum value of tau m is denoted by tau max, so tau max is the maximal traveling time across the array, the narrowband assumption implies that during this traveling time, so during the time the waveform travels across the array, the signal does not decorrelate. The signal remains almost completely correlated. So small bandwidth, slow time variation. In particular, we don't observe a significant variation of the signal during the traveling time across the array. So the wavefront remains fully correlated when it passes across the array. And this is an assumption that we can make if the signal is narrowband. Okay. So if the signal is narrowband, instead of alpha of t minus tau m, we put alpha of t. Instead of phi of t minus tau m, we put phi of t. So what is the effect of a delay? The effect of the delay is just this term here. So if the signal is narrowband, a delay is mapped into a phase shift. So we have a phase shift that is proportional to the delay. Otherwise, this approximation, so if the signal is not narrowband, this approximation is not valid. Now, under this approximation, the linear convolution between the received signal and the impulse response can be basically simplified. Because if you assume that the signal, the input signal is very narrow around the central frequency, the effect of passing through a linear time invariant filter is that the amplitude is modified by this term, which is the frequency response of the sensor calculated at the central frequency Fc, and this is the phase response calculated at the central frequency. So again, a delay is mapped into a phase shift. Now, we can express the signal, the real narrowband signal at the output of the sensor in terms of what is called complex envelope. So the complex envelope, so I mean, the real signal can be expressed in terms of the complex amplitude as the real part of the complex envelope multiplied by e to j to pi fct, where fc is the central frequency. Now, if this is y tilde, the complex envelope is given by this expression here. Now, also the noise can be represented through its complex envelope. So W tilde is the real noise, W is the complex envelope of the narrowband noise. And so in other words, the complex envelope under the narrowband assumption can be expressed in this way. So you have alpha of t, you have the gain or attenuation introduced by the sensor, which is the modulo of the frequency response of the M sensor at the frequency fc. Then you have the phase shift induced by the delay. Then you have phi of t, and then you have the phase shift induced by the sensor. So, I mean, we can write these things together. So this term here is the complex envelope of the received signal that I call S of t. So S of t is the complex envelope of X of t. So I'm assuming that you know what is the complex envelope of a signal, because it's a very important tool to represent narrowband real signals. So I will not spend time in defining the complex envelope. I assume you have this knowledge from signal theory. And then we have the frequency response of the sensor. So at the end, the complex envelope of the signal at the output of the M sensor can be expressed in this way. And I repeat, this term tells that a delay is mapped into a phase shift. At this point, so at the output of each sensor, we extract the complex envelope. So we implement that operation that in signal theory is called demodulation. So we obtain the complex envelope. The real part of the complex envelope is called in-phase signal. The imaginary part is called quadrature signal. We sample at interval Ts, so Ts is the sampling interval, and we collect n samples. So Ts multiplied by n is the observation interval. So during the observation interval, we collect n samples by sampling at intervals Ts. So basically, Ymn is the space-time signal, because n is the discrete time. M is the space index, because it refers to the M sensor that is located in a different position. So the variable M basically takes into account of the spatial sampling, and the variable N takes into account of the temporal sampling. So the space-time signal can be expressed in this way. So we have the frequency response of the M sample of the M sensor calculated at the central frequency of the received signal. We have the phase shift induced by the delay by which the signal is received at the M sensor. We have the complex envelope, S of n, of the narrowband signal generated by the source, and then we have the disturbance. And the two indexes n and m refer to the time and space. So we have n temporal samples, and we have m spatial samples that corresponds to the location of the m sensor. Now, the block diagram of the receiver that implements the modulation operator, so the extraction of the in-phase and quadrature component is basically reported here. So we have an oscillator. By using an Hilbert filter, we built an oscillation in quadrature. So we multiply the incoming signal by the cosine and the sine. Then we send, after mixing the signal to a low-pass filter, we obtain the in-phase and quadrature signal, and then we sample the in-phase and quadrature signals. And so we obtain basically the real part and the imaginary part of the complex envelope by using this double branch receiver with the in-phase branch and the quadrature branch. So the complex envelope represent two real signals that are obtained in the in-phase superior branch and quadrature inferior branch. And this is the expression. So the most important thing that should be understood is that if the signal is narrowband, the effect of the delay, so we receive the signal with the delay tau m, the effect of the delay on the samples of the complex envelope is a phase shift that is represented by this term. And this is the fundamental fact. Now, let's arrange the m spatial samples in a m-dimensional vector. So the y bold represents the m-dimensional vector that contains the m samples at the output of the m sensor at time n. So the m samples that we collect at time n. So this vector is called snapshot or temporal snapshot. And the size of this vector is equal to the number of sensors in the array. Now, if you collect for a given n, the m values of this, basically S of n does not depend on m. So you can put in evidence. And so what remains is this term here calculated for m equal to 1, m equal to 2, and so on. M equal to capital M. Now, the elements of this vector that I call A depends on the delays, but the value of the delays, as you will see, depends on the direction arrival. So in other words, this vector depends on the direction arrival of the target, of the source. So I make this explicit by saying that A is a function of phi t, the elevation, and theta t, the azimuth of the target. So y bold is equal to A bold that multiplies the complex scalar S of n plus noise. Obviously, the noise is additive. So the signal vector is proportional to vector A, and vector A depends on the frequency response of the M sensors and the delays depends on the geometry of the array. So the vector A basically is known when the array is calibrated. So if the array is calibrated, it means that we know this vector A. And this vector A is called spatial steering vector, or sometimes it is called also array response, because it's a vector that tells you what is the signal at the output of the array when a source generates the signal with the complex envelope S of n. So S of n is the input. This vector is the output of the array. So it is the array response. That's why it is called array response. Clearly, I mean, these frequency responses should take into account also the directionality of the sensor. So if the sensor is directional, so it depends not only on the frequency, but also on the directional arrival. So, I mean, for easy annotation, I did not report explicitly this dependence. But if the sensors are omnidirectional, the frequency responses do not depend on the directional arrival. So remember, A is typically called spatial steering vector, or sometimes array response. Now, how do we find the relationship between the directional arrival and the delays? Because remember, at the end, we want to estimate the directional arrival. But the dependency of the received signal on the directional arrival passes through the tau k. Now, this relationship depends on the array geometry. So, to make this evident, let's assume that the array is uniform and linear. So linear means that all the elements are aligned over a line. Uniform means that the distance between adjacent sensor is the same. So if you have an array like this, it is called ULA, Uniform Linear Array. So ULA is the acronym for Uniformly Linear Array. So let's derive the relationship between the directional arrival and the delays under the assumption that the array is ULA. So phi is the elevation, theta is the azimuth. Now, let's denote by k hat the vector, so the unit norm vector that points in the direction of propagation. So let's assume that the propagation, the direction of the propagation of the planar wavefront is characterized by these two angles phi and theta. The vector k hat can be expressed in this way. Cosine phi sine theta. This is the versor along the x direction. Cosine phi cosine theta. This is the versor along y direction. Sine phi iz. So these are the unit vectors, so versors, in the Cartesian coordinate system. So in other words, so let's assume we have an active radar, but if it is passive, it's the same. So this is the direction of propagation from the radar to the target and back. And let's assume that it points from the radar to the source. So this is the elevation phi, and this is the azimuth theta by definition. So if you watch the geometry from above, so let's assume that the array is Euler aligned along x, and the array can even move, and this vector is the velocity vector. The source is in this direction, so the azimuth is the angle between the vector k hat that points in this direction and the vertical to the array, which is the direction y. So the azimuth, by definition, is the angle between the vertical to the array and the propagation direction. Okay. Now, if you assume that the Euler ray is aligned along x, the vector that expresses the position of the M sensor as component only along x, so the position vector can be expressed in this way. So in the origin, we have the reference signal, the reference vector, and then at distance d, we have all the other sensors. So the position vector is m minus 1 d. D is the distance between adjacent sensors that multiplies the versor ix. And this is true for m that goes from 1 to capital M. Now, what is the delay between sensor 1 and sensor m? You can understand from this figure. For example, what is the delay between sensor 1 and sensor 2? This is the space that should be traveled from sensor 1 to sensor 2. So this is the wavefront. This is the propagation direction orthogonal to the wavefront. This is the additional space that should be traveled. And this space is what? Is the component of the distance along the propagation direction. So it is this quantity here. So if this is the azimuth, this angle is exactly the same as the azimuth. So if the distance between 1 and 2 is d, this length here is d sin theta. And so the delay is d sin theta divided by the propagation speed c. Now, the propagation speed is typically known. So we know the propagation speed in free space, in water, and so on. Now, in general, how can we express this space here? It is the component of the direction vector along the direction of propagation. So it can be obtained as the inner product between k hat and Rm. So this symbol is the inner product. And if you calculate the inner product between these two, obviously, because R of M has component only along X, basically the only part of K that contributes to this inner product is the component along X, is this one. So you replace R of M with this definition. You replace K with this definition. You calculate the inner product, you get this. So you get M minus 1 that multiplies the distance d divided by the propagation speed. And then you have the cosine of the elevation multiplied by the sine of the azimuth. So for a Euler array, this is the relationship between the direction of arrival and the delay. If the geometry is different, it's not Euler, R of M will have a different expression, and when you calculate the inner product, you will get a different relationship. If the array is Euler, this is the expression of R of M, and this is the relationship we were looking for. Now, as you remember, the central frequency Fc can be expressed also as the ratio between the speed of propagation in free space, it is the speed of light, divided by the wavelength. And if you define as Fs, which is called normalized special frequency, d over lambda cosine phi sine theta, I mean, this is an adimensional quantity. So it is called normalized target special frequency. And you can observe that if you define the product of cosine sine as sine of psi, this psi is what is called conic angle. So you can understand that if from an estimate of the delays, we can estimate Fs, because there is a relationship. But once you have estimated Fs, you cannot retrieve separately the azimuth and the elevation, but what you can get from Fs is only the so-called conic angle. So there is an ambiguity. So in other words, if you have a Euler array, you can't estimate separately the azimuth and the elevation, but you can estimate only what is called conic angle. That is an angle psi that depends on the direction of arrival through this relationship reported here. Now, typically, we use a linear array when we are interested on estimating only one angle. That can be the azimuth or the elevation, but not both. So we cannot estimate both by using a linear array. So let's assume, for example, that we know the elevation. For example, we want to detect a boat on the sea surface, so the elevation is 0. If we can assume that the elevation is 0, so in other words, the target, the source, and the array are on the same plane, in that case, if the elevation is 0, the relationship becomes this one. because cosine of phi is equal to 1. And so in this case, the conic angle coincides with the azimuth. And so we get an estimate of the direction arrival by estimating the azimuth, because all the geometry is planar. Okay. So remember, this is very important. By using a linear array, you can't estimate separately azimuth and elevation. You can only estimate the angle for, you have to consider this geometry. So the plane the plane that contains the source and the linear array, and the only angle that you can estimate is the angle between the direction arrival and the vertical to the array. This angle can be either the azimuth or the elevation, depending on the orientation of the linear array, but you can't estimate both. You have to assume that you know one of the two and you estimate the other. If you want to estimate separately azimuth and elevation, you need a planar array or a conformal array or a volume array. Okay, so in the case of uniformly linear array, this is the relationship between the delay and the direction arrival. You can express in terms of the digital frequency normalized spatial frequency Fs. And if you estimate Fs, you can get an estimate of the azimuth through this relationship. Fs is d over lambda sine theta t, where theta t is the azimuth of the target of the source. So if you express the array response in terms of the spatial frequency, you get these results here. So you express, you replace tau 1, tau 2, and so on, and you express in terms of the spatial frequency. Okay. You can also, because the spatial frequency depends on theta t, basically you can say that the array response depends on the direction arrival. Now, if you assume that all the sensors are identical, so the frequency response is the same, and this is something that we always try to do. So when we build an array, we always try to build the sensor in such a way the frequency response is identical for all of them. So if you can make this assumption, you can bring the frequency response outside. This is a complex scaling factor. So basically, you can absorb this complex scaling factor in the signal complex envelope. And in terms of terminology, obviously, this is a vector. For different values of theta, you get a different vector. The collection of all the array response that you get by changing the parameter theta provides what is called array manifold. So the array manifold is the set of all the stream vectors that you obtain by changing the parameter theta. And because A depends on theta in a different way for different geometry, Basically, the array manifold depends on the array geometry. The array geometry determines the array manifold. Okay. Now, if you use a Euler array, basically we are sampling in space the signal uniformly. So if you think, this is very similar to what we do in the time domain, when we sample in time uniformly. The only difference is that now the sampling is in space. So how do we implement the uniform sampling in space? By building a Euler array. Now, if you think the sampling theorem, the Shannon sampling theorem, if you remember, the condition that guarantees that when you sample, you don't lose information, the condition is that the sampling frequency, Fs, is at least twice the bandwidth of the signal. So the signal should be with limited bandwidth, and the sampling frequency should be at least twice the bandwidth. Now, if you start from this relationship, which is stated by the Shannon theorem, and you express in terms of B divided by the sampling frequency, so you get that the bandwidth normalized to the sampling frequency should be smaller than 0.5. So this is the statement of the Shannon sampling theorem. Now, if you think about the similarity between temporal and spatial sampling, it's obvious that it must exist a sampling theorem for the spatial sampling. And the sampling theorem, if the sampling is uniform, cannot be different from this. So this is the normalized frequency. So the highest normalized frequency in the signal, and this should be smaller than 0.5. Okay, in our case, the normalized frequency is Fs, and basically we should have the same inequality. This quantity should be smaller than 0.5. Now, because this normalized frequency can be positive or negative, we need the absolute value. It can be positive or negative depending on the value of the azimuth. So the modulo of the normalized frequency Fs should be smaller than 0.5. But the modulo of the normalized frequency is d over lambda modulo of the sign. Now, the sampling interval here is d, remember. So the sampling in time is made at interval ts. The sampling in space is made at intervals d. So the sampling interval d should be selected in a way that the spatial Shannon sampling theorem is satisfied, this one. Now, because it depends on the azimuth, well, we can say that I select D in order this inequality to be satisfied in the worst case. And the worst case is when this quantity is the largest. So it means theta equal pi over 2. So the largest value of the modulo of sin theta is 1. So basically, I select D in such a way that this inequality is satisfied in the worst case. And so what I get is that the distance between the sensors cannot be greater than half the wavelength. So I can space the sensor more than lambda over 2. Otherwise, I will have aliasing. Aliasing in space is different than aliasing in the time domain. And you will see that aliasing in space is equivalent to grating lobes in the array pattern, but we will see later this. So if I want to avoid aliasing, which is a distortion, D should be smaller than lambda over 2. Now, because the signal is not monochromatic, but it has a finite bandwidth, this relationship should be satisfied for the minimum wavelength. So the minimum wavelength corresponds to the maximal frequency. So the signal has a finite bandwidth. F max is the maximal frequency. From the maximal frequency, you get the minimal wavelength. Then the spatial Shannon sampling theorem says that the distance between sensor should be smaller than 1/2 of the minimal wavelength. If you don't satisfy this constraint, you will get aliasing. So you will get a distortion. And we will try to understand better what is the effect of not respecting this inequality. Okay, we will see later. Now, if you remember, we assume that the sensors are linear. So if instead of one source, there are k sources, because you can apply the superposition principle, if all the receivers are linear, if at the input of the array you have the superposition of the signals generated by k sources, at the output of the array, you have the superposition of the output. So you have the summation for k that goes from 1 to the number of sources or the number of targets of A of theta k. So you have theta k, and theta k is the kth direction of arrival. So the direction of arrival of the kth source multiplied by this signal generated by the kth source. So remember, we are talking about complex envelope here. So this is the complex envelope of the signal at the output of the array when in the environment we have k sources or k targets. Now, this summation here can be expressed in compact matrix notation if you define the so-called steering matrix. So the steering matrix is a rectangular matrix of size m times k. Remember, m is the number of sensors in the array. K is the number of sources. So how do you build the steering matrix? The first column is the array response calculated in the direction arrival of the first target. The second column is the array response calculated at the direction arrival of the second target, and so on. So you have k targets, k sources, k column. So you can denote by theta bold the k-dimensional vector that contains the k direction arrival. If the array is Euler, we have k normalized special frequencies defined the usual way. And then you can define the vector S that is k-dimensional. So the size of S is equal to the number of targets. So at the end, the array equation in the presence of k sources can be expressed in this way, in compact matrix notation this way. So Y is m-dimensional. Matrix A is m by k. S is k-dimensional. W is m-dimensional. And this is the expression of one snapshot. So we sample at n times, capital N times. So we collect capital N snapshot, each one with this structure. And typically, the goal is estimate
Excuse me,
the
sir.
directional arrival of the targets and reconstruct the k different signal generated by the k different sources.
Excuse me, sir.
Yes,
Sir, can we have a break of 30 minutes as per schedule?
yes. I mean, I wanted to arrive here.
Okay, sir.
This
Okay,
is the
sir.
perfect time to have the long break. So half an hour, okay?
Okay, sir. Thank you so much.
Okay, thanks. I think we can start again.
Yes, sir.
Yes, we can start.
Okay, so we derived the data model. So the vector y is an m-dimensional vector. So the size of y is the same as the number of elements in the array. And for each time n, it can be expressed as the product of the steering matrix multiplied by the k-dimensional vector that contains the signals generated by the k sources plus additive disturbance, which can be thermal noise, but also clutter and interference. And typically, we observe the signal over the observation interval, and we collect n, capital N, temporal snapshots. Now, the problem that we typically want to solve is, given the observation of n snapshot, we want to estimate theta, and we want to reconstruct separately the signals generated by the different sources, or we want to analyze separately the signals reflected back by the k different targets. So once we have separated, obviously the processing that we do in the time domain is different according to whether the system is passive or active. If it is passive, typically we do spectral analysis to understand the property of the source and classify the source. If we are in an active sensing scenario, we do matched filtering and we estimate the range and the Doppler frequency of the target, and so on. Now, to fully characterize the statistical behavior of this vector, we should know the joint PDF, the joint probability density function. Typically, we make this under the assumption that the disturbance W is Gaussian. The signal is typically zero mean. So if W is Gaussian and S is either Gaussian or deterministic, the vector Y is Gaussian. So its probability density function is completely determined by the array correlation matrix or array covariance matrix, because if the process is zero mean, correlation or covariance is the same. If W is non-Gaussian, things becomes much more difficult. And most of the time, we design our algorithm by using only second-order statistics. So we neglect the non-Gaussian distribution of Y, and basically we analyze only second-order statistic. And if the process is zero mean, obviously the second-order statistic that matters is the array correlation matrix or array covariance matrix, because I repeat, since Y is zero mean, correlation or covariance is the same. So by definition, the spatial correlation matrix, which is an M by M square matrix, is defined as the expectation of Y of n, Y Hermitian of n. We need the Hermitian because we are talking about complex envelope. So the signal is complex. So Y Hermitian is the transpose of Y conjugated. So this is the definition of the spatial correlation matrix. So basically, on the main diagonal, we have the powers of the signal at time n at the output of each sensor. Off diagonal, we have the spatial correlation at time n between samples collected at the output of different sensors. So it's the correlation between different sensors at the same time. So it is the spatial correlation. Now, because the signal is signal of interest plus disturbance, and because the signal of interest and disturbance are always independent, they are also uncorrelated. So it means that the cross correlation between the signal and disturbance W is 0. And so if you calculate explicitly the spatial correlation matrix of the output of the array, so Ry, so you have signal of interest plus disturbance that multiplies the same quantity Hermitian. Now, because S and W are uncorrelated, all the cross terms are 0. So the correlation matrix of the sum is the sum of the correlation matrices. So the correlation matrix of the signal, the first term, plus the correlation matrix of the disturbance, second term. Now, okay, let's define Rw, the correlation matrix of the disturbance. And I repeat, disturbance is thermal noise, clutter, and interference. As concerning the signal, we have this term that multiplies its Hermitian. When you calculate the Hermitian of AS, you get S Hermitian, A Hermitian. Now, the next step is, because A, the steering matrix, is deterministic, you can bring outside the expectation. So you bring outside the expectation on the left and on the right. So you remain with the expectation of S as Hermitian. By definition, this is the K by K spatial correlation matrix of the K signals generated by the K sources. So this is the correlation matrix of the signal, and this is the correlation matrix of the noise. Now, typically, the number of sensors M is greater than the number of targets K. So A is an M by K matrix. Rs is K by K. A Hermitian is K by M. The rank of this matrix, the rank of the product of the three, basically is at most equal to K. So if A and R are full rank matrices, the rank of the signal matrix is equal to the number of targets, K. So the rank of the signal matrix, I repeat, coincides with the number of targets. So if you are able to estimate the rank, so the number of non-zero eigenvalues, you can get an estimate of the number of targets. Plus the disturbance correlation matrix, which is typically a full rank matrix. And I mean, this difference in structure is very important, because this difference is what allows you to separate signal of interest from disturbance. Now, let's assume that the noise is partially white. So not always it is white, but I mean, thermal noise for sure is spatially and temporally white. So let's assume that the noise is spatially white. Spatially white means that the correlation of the disturbance between different sensors is 0. So the disturbance is uncorrelated from one sensor to the other. So if it is white, the correlation matrix of the disturbance is the disturbance power that multiplies the identity matrix. Now, if we don't want to use the PDF of the data, maybe because they are non-Gaussian and we don't know the PDF, we should rely on the structure of the correlation matrix to design our algorithms. This information, so second-order statistics, the autocorrelation matrix, unfortunately is typically unknown. So what we have to do is to estimate the sample covariance matrix, sorry, to estimate the correlation matrix. And one possible estimator, as you probably know, is the sample correlation matrix. So we have n snapshot. We can't calculate this expectation. We replace the expectation with the arithmetic average over time. So if we do this, so we average this quantity, the quantity that was inside the expectation, we average over time. We calculate the arithmetic mean. We sum these n matrices and we divide by n. So this is called sample correlation matrix, and it is denoted by the acronym SCM. It's an estimator that belongs to the family of sample estimator, and under some weak conditions, we know that it is consistent. What does it mean that it is consistent? It means that when the number of snapshots tends to infinity, the sample estimator tends to the true correlation matrix. So the error tends to 0 when the number of collected snapshots tends to infinity. In general, this is not the best possible estimator. The best possible estimator typically is the maximum likelihood estimator. The sample correlation matrix is also the maximum likelihood estimator only if y is Gaussian. If y is not Gaussian, the sample correlation matrix estimator is still consistent, but not the best possible. But typically, we continue to use the sample correlation matrix estimator because it's very simple to implement. Instead, in non-Gaussian signal, the maximum likelihood estimator of Ry is very difficult to obtain, and most of the time cannot be obtained in closed form. So, in other words, we tend to use this estimator both in the case that y is Gaussian and in the case that y is non-Gaussian, and maybe with unknown distribution. The signal detection problem can typically be stated in as a binary hypothesis testing problem. So in the null hypothesis, what we observe is only disturbance. And in the hypothesis H1, what we observe is disturbance plus signal of interest. And I mean, included in the signal detection problem is the problem of estimating the number of sources. So the capital K number of sources. There are a number of different methods depending on the assumption. These methods belong to the family of model order selection methods. I don't have time in this week to talk about MOS methods, but I will say something. So let me defer how to estimate K later on in the course. Mm. So let's assume that we have applied one method. So we give the data to this method, and the output is an estimate of K. At that point, we want to estimate the K direction of arrival, and we want to separate the signal generated by the K different sources, or we want to estimate the parameter of the K targets. So the range of each target, the radial speed of each target, and so on. Okay, now let me spend some words on how to complicate the model if some of the assumptions that we made are not valid, or, I mean, they are never perfectly valid. But, I mean, the model that we adopt cannot be too complex, because otherwise it becomes useless. So the choice of the mathematical model should be always, always, always a trade-off between complexity and accuracy in the description of the physical phenomenon. And typically, if you want a model that is very, very accurate, it becomes very complex, and so it becomes useless. So it's important to be able to understand what could be a good trade-off. Now, what are the, in radar, I'm talking about radar because I'm more familiar, obviously, on radar application. So what are the most important reasons why, in reality, the data deviate from the model that we derived so far? This model is quite simple, and I mean, we derive it under some assumption, and I repeat, none of these assumptions are perfectly valid. They can be more or less accurate, but never perfectly valid. But believe me, many important methods that are applied in practice have been derived using this simplified model. So this model is very useful. Sometimes some of the assumptions are really far from being realistic. In that case, we have to complicate the model. But I mean, the model that we derive is a good starting model. Okay. Now, one effect that show up in reality is the mutual coupling effect. So basically, mutual coupling means that when you put two sensors too close, the behavior of one sensor is influenced by the presence of the other sensor. So there is a mutual influence that is called mutual coupling. And the model that we derive does not properly account for this effect. And I repeat, the mutual coupling cannot be neglected if the sensors are too close. If they are spaced enough, you can neglect. Now, people have studied the mutual coupling, and they found that the mutual coupling effect can be taken into account by modifying the spatial steering vector in this way. So you start from the ideal steering vector that we derive, that, remember, it is known if the array is calibrated. So if we know the geometry of the array and we know the frequency response of each sensor. To take into account the mutual coupling, you can multiply the ideal steering vector by the so-called coupling matrix C. So the coupling matrix C model the effect of coupling between different sensors. Now, the problem is how to derive C. Now, for very simple geometries, for example, Euler array, C has been derived theoretically. In most of the cases, C cannot be derived theoretically. And so what people do is they measure experimentally the new steering vector, C of theta, so this is a vector. So you measure this experimentally. You transmit a signal that you perfectly know, and you measure the response of the array. And what you measure takes into account of all the non-ideality, because it's what you measure. So it takes into account of everything, and in particular, it takes into account of C. So in other words, you measure the array response experimentally. Once you have the measure array response, you use the measure array response to process the signal collected during the normal operational period. Now, what are the most important sources of non-ideality? One is that we don't know exactly the position of the sensor. So their position can be slightly different from the nominal one. And in addition to that, if the sensors are not omnidirectional, also the orientation is important, and maybe we don't know exactly the orientation. So this is a source of non-ideality. So in this case, the array is only partially calibrated, because we know the nominal position, but there is an error. So the array is only partially calibrated in this case. The other source of non-ideality is the fact that the frequency response of each sensor can be slightly different. Not completely different, obviously, but nominally the frequency response, so the amplitude and the phase of the frequency response nominally are the same. In practice, when you build them, they are slightly different. And so these are called channel imbalances. Then within each channel, you can have imbalances between the in-phase and the quadrature channel. You have seen that to extract the complex envelope, we have to implement the in-phase and quadrature channel. And there are two filters, one in the I channel, the other in the Q channel. The two filters, low-pass filters, should be exactly the same. And maybe they are only nominally exactly the same. The other source of non-ideality can be due to the fact that the filters, and in particular the amplifiers, does not behave exactly as linear time invariant systems, but they can introduce nonlinear distortion. The same, the L02 converter or the modulators. And then we can have multipath phenomena, especially if you have, for example, a radar mounted on a ship. So we can somehow take into account of all these imbalances, complicated the model, so complicating the expression of the array response. But most of the time it's so difficult to model all these non-idealities that, I repeat, what we do is we inject in the system a perfectly known signal, and we measure the real array response. So we measure A of theta experimentally, and we use the measured one in place of the ideal one to perform all the processing. This operation obviously is called calibration. And there are many methods of calibration: self-calibration, external calibration. I don't have time to enter in this detail. So if you are curious about this problem, you can search on IEEE Explore or Wikipedia array calibration, and you can find different methods. I will say something about a particular source of non-ideality. And this is the case where the sources are not point-like, but in practice, all the sources are composed by a number of scatterers distributed over a space. In that case, the contribution from each scattered some, but because the phase is not exactly the same, basically this introduces some fluctuation, and the same kind of fluctuation can be introduced if the propagation medium is not ideal, and it introduces distortion in the waveform.